Hello everyone and welcome to this lecture. In the last lecture, we saw brief introduction about eigenvectors and eigenvalues. Okay. In this lecture, we will start with the question of finding the number of walks of length k between any two vertices. Okay. And we will see that answer to this question lies in matrix product. Okay, and then we will further see that the matrix product can be computed using eigenvalues. Okay, at the beginning it looks quite surprising that a graph theoretical question we are able to answer in terms of matrix product, and then matrix product can be simplified for at least certain kind of matrices using eigenvalues. So lot of interesting stuff is ahead of us. So let us start. So I will be taking the same example that I have taken in the beginning of in first lecture, second lecture, and maybe in the beginning of third lecture. Okay, so let us take the same example on a graph on 4 nodes. So suppose this is 1, 2, 3, 4, and I think the edges were, yeah, so these were the edges, right? If I ask you how many walks of length 2 are between vertex 2 and 3, suppose vertex 2 and 3, right? How many walks of length 2 are there? So let us see how many. Okay, I think there is just one walk. Okay, and maybe this is this. Is there anything else? No. In fact, this is a path also, right here. Let us ask some. Let us ask a different question. How many walks of length 2 are between vertex 1 and 3? Okay, vertex 1 and 3. So let us. So right now it was coming out to be 1. Between 1 and 3, how many walks of length 2 are there? So one way is this, right? 1. Oh my god, again maybe they are just path also. I deliberately want a walk which is not path. Okay, so 1, another one is this one. 2, is there anything else? No, if we go by this, yeah, but if go back. No. Okay. Now, I mean, again, I think if I am correct, so then this is again 2, sorry, this is 2. Again, both of these possible ways are of length 2, and these both are path basically. Now, let me, maybe I will tell you some different example, I mean different question. So, suppose I want a case where these paths are repeating. Basically, sorry, path not, edges are repeating. In that case, the path will be walk, right? Okay, so by the way, path is also a walk. So till now, I'm not doing any mistake. I just want, I mean, more generalized case where walks, where the edges are repeating, come into picture. Let me ask, how many walks of length 3 are, length 4 are between vertex and 3? Now, so this is about length 2. Suppose the same question I ask between vertex n and 3, how many 4 length walk? Length spelling is 4 length walk. Okay, so how many are there? So let me pictorially write here 4 length, right? Yeah, so 1, 2, yeah, 3, and again you go to 4. Okay, so this is one walk of length 4. Another walk is, I mean, maybe similarly 1, 2, 3, and 4. Okay. Okay, I hope this, maybe there are more, maybe there are 1, 2, okay, wait, 1, 2, 3, 4, no, this is no. So maybe you can, I mean, maybe there are some more, I'm not sure. But what if I tell you the matrix product can give these numbers? Right now I will not say quickly, yeah. Later we will say that the matrix product indeed will give you quickly. Okay, so let me first write a theorem or a beautiful result which actually establishes this fact. Okay, so let me first write this statement. Okay, so before that I need to define what is adjacency matrix. By the way, till now I have defined the incidence matrix. Okay, then Laplacian matrix. Laplacian matrix is nothing but incident matrix times its transpose. Okay, on the diagonal there were degrees, on the off diagonal whenever there were edge between vertex I and j it was -1, otherwise rest of the entries are 0. Okay, so what is adjacency matrix? Adjacency matrix is in fact much more simpler. Adjacency matrix is there. So a matrix A is called adjacency matrix of order n cross n. So this is corresponding to some graph G in which there are n vertices. Suppose this is my graph, and then this is my graph. So let me remove this. This is not, yeah, okay. So number of vertices here is n. So a and n, so let me write some generalized entries to be aij. Okay, so aij is equal to 1 if vertex I and j has an edge between them. Okay, otherwise 0. Very simple. So what will be the adjacency matrix of this? Okay, so this graph, the adjacency matrix will be this. Okay, so firstly on the diagonal there will be zeros. Okay, so because there is no self loops, right? So 0, 0, 0, 0, and then you talk about other. Okay, so 1, 2 there is an edge, 1, 2 there is an edge, 1, 3 there is no edge, 1, 4 there is an edge. Okay, now see the matrix, the graph is undirected. So if I j edge is there, j I j edge is out there. Okay, so I can simply say this will be equal to 0 and 1 because matrix will be symmetric. Okay, now between 2, so it is connected to the rest of this. So what is this? So this will be also this will be 1. This is symmetric, and maybe immediately you can see some properties of this matrix also. If you add each row or each column, right, you will get the corresponding degree of the vertex. Okay, very good. So this is very good. Now let me write the theorem. Okay, the result, very nice one. Okay, so theorem is this. Okay, let G be a connected graph okay, the number of walks length k between vertex I and j, vertices I and j is given by what? A to the power k I comma j. The ijth entry of a to the power k. Okay, so for example, if I have to find the number of walks of length 100 between vertex 2 and 3, then what will be that number? That number will be the 2/3 entry of a to the power 100. Okay, so let us try to prove this. Why this follows? Okay, yeah. So proof. How can you prove this? Okay, proof is actually, I would say, very simple. Okay, so till now everything was ideally very simple. Sometime the things when we were doing in finding the expanding, the things were slightly counterintuitive, but otherwise I don't think there was any difficulty here. So I mean, I will try. I mean, your job very, very easy, but sometime things will getting more involved, but right now the things are very, very simple. Okay, so we will prove that this statement is true using mathematical induction. Okay, and then we will induct on k, number k. Okay, so for so let us start with induction on k. So when k equal to 1, okay, so the base case is when for k equal to 1, okay, is this theorem true? So what will be this theorem for k equal to 1? This will be what? See, for k equal to 1, this matrix is nothing but the adjacency matrix, right? A to the power k is nothing but adjacency matrix. So it will be nothing but, so a to the power k is nothing but the adjacency matrix. A to the power k is the adjacency matrix. Okay, and by the definition of adjacency matrix, by the definition that the way we have defined, it indeed gives the number of walk of length 1, where k equal to 1, right? Number of walk of length 1 between any two vertex. So basically here, okay, so what is the walk of length 1? How many numbers of walk of length between 1 and 3 are there of length 1? There is 0, right? So 1 and 3, right? It's actually captured by the adjacency. Whenever there is an edge between vertices, that means there is a walk of length 1, right? You can go but direct from I to j through that edge. So this is just walk of length. If there is no edge between vertex I and j, there is no walk of length. So it's a 0, right? So the number is 0. So for k equal to 1, this is indeed true, right? Now we will assume that the next step of induction is hypothesis. So we will assume that. So this is for base case, right? Let me call it, the base case. This is base case. Next, let us assume that this is true for some k greater or equal to 1. Okay, so this is now my assumption that suppose the statement holds for k greater or equal to 1. Okay, and then I will prove that this holds for k plus 1. Okay, so that means what? That means this. So the number of walk of length k between vertex I and j are given by this quantity, right? So by this number. Okay, now we will prove that the number of walks of length k plus 1 between vertex I and j are given by a to the power k plus 1 and ijth entry of it. Okay, so let us analyze this, why it happens. Okay, so suppose you have a path of length k plus 1 between vertex I and j, right? Suppose this is a path. Suppose this is a path of length k plus 1. I can decompose this path into two parts, where there is a vertex along this path which is just adjacent to j. Suppose this vertex is u. Okay, suppose this vertex is u, right? Then what will be the length between vertex I and u? It will be of length k, right? Now there can be actually many paths which are reaching to u in length k, in length k. Sorry, not path, walk, right? Between length. And this number is given by what? By our induction hypothesis, right? And in this way, maybe there will be, like u, there will be many other vertices. There are many other vertices which have direct edge. Basically, they are neighbors to j, such that these neighbors may also have a path of length k. I'm again saying path, but it should be I leave a walk, right? Okay, sorry of this mistake. So it's a walk. Okay, again, and so on. Okay. Now, if you carefully look at it, I mean, you will get some intuition why matrix product thing is coming into picture here. Okay. See, up to, suppose for example this, yeah. Okay. What will be this quantity? So this will, suppose this, a to the power k, I and u. Okay, this will is by induction hypothesis giving you what? The number of walks of length k between vertex I and u. Okay, now suppose there is an edge between u and j, right? So that means what? Adjacency matrix times u and j. This will be 1 only when there is an edge between u and j. So this quantity will also give the number of walks of length k plus 1 which are going through u between vertex I and j. Okay, now like u there can be many other vertices, right? So if I sum over those u's, this will indeed give us the total number of walks of length k plus 1 between vertex I and j. So basically if I sum over all u such that, in fact, yeah, so I mean I can write very safely that u equal to 1 to n, right? See, whenever there is a walk, the number of walks between I and u of length k are there, right? The number of k length walk between I and u, and then you multiply with the uj entry of the adjacency matrix. This will indeed give you the number of walks of length k plus 1 which are going through u. Now, if you vary u over all the vertices, it will indeed give you total number of walks of length k plus 1, right? Okay, very good. Maybe sometime u and j do not have an edge, right? In this case, I mean this k plus 1 length will not be counted. If there is an edge here and there is a path of length k between vertex I and u of length k, this will be counted, right? This is very beautifully, this quantity is very beautifully captured by matrix product. Okay, how? If you see that this is nothing but the quantity a to the power k plus 1 I and j. Proved. Okay. Now what about closed walks? Remember what were the closed walk? Closed walk was a walk that is started at some vertex and ends at the same vertex. Okay. So yeah. Now closed walk will be what? Closed walk will be nothing but when you I equal to j basically, right? Very good. Now the next obvious thing is I am boasting too much about this matrix, right? Matrix power or matrix multiplication. I mean, how can it be? I mean, this question be relevant that suppose I want to count a walk of length 1000 between vertex I and j, I have to find the a to the power 1000, right? And suppose matrix is big, right? How I can do it? I mean, this is, suppose I have to calculate this matrix. How I will do it? Some of you might be very clever here. Oh, I mean, maybe we can do divide and conquer things. So suppose if I somehow calculate a to the power 1000, a to the power 500, then I have to multiply with just one more matrix because I already find a to the power 500, then I will multiply this with same matrix. But then next question, how you will find 5.9? Then you will, let us find a to the power 250 and so on. A to the power certain number, right? So log of that number will give you the number of matrix product. But is there more clever way? Is there a more clever way? The answer is yes. But for that cleverity to happen, the matrix has to be following certain properties, and fortunately for this course, and right now at least for this topic, the matrix that we have what? We have adjacency matrix. Okay, I told you symmetric matrices display very beautiful properties. Adjacency matrix is also symmetric matrix. For this matrix, right, eigenvalues and eigenvectors makes our life super easy. Okay, so we will see in the next lecture that that eigenvalues and eigenvectors can, directly can give the number of walks of certain length between vertex I and j. Okay, and before ending, let me give you a question. How will you find the number of triangles in a graph? How will you find number of triangles? Then the next question is, how will you find the number of C4 cycles? So triangle is what? Triangle is this. So we will denote it by C3. Similarly, C4 is there. So how will we find this in a graph? Okay. So think about this question. Okay. So we will meet in the next lecture, and then we will see some remarkable use of eigenvalues and eigenvectors. So till then, thank you very much.